Hi, today's topic is Postulate 4 of quantum mechanics, which is closely tied to what is known as the measurement problem. Postulate 4 states that measuring a quantum system causes the wave function to collapse. In other words, the system shifts from a probability distribution of possible outcomes to a single well-defined value, at least for a short time. Before discussing the measurement problem, I will begin with a brief summary of key results from the first three postulates, and then move on to discuss Postulate 4 in detail. Postulates 1 through 3 of quantum mechanics define how a wave function represents the state of a quantum system, and how measurable quantities yield real outcomes with probabilities determined by the wave function. In quantum mechanics, the wave function contains all the information about the system. The main objective in quantum mechanics is to determine the wave function. Once you know it, you know everything you can know about the system. The wave function is the complete description. Postulates 2 and 3 discuss observable quantities. Physical quantities such as position, momentum, and energy are not deterministic. They are described by probability distributions and represented mathematically by Hermitian operators. In classical physics, things have a definite value. A ball has a specific position and speed, but in quantum mechanics, those values are fuzzy and spread out over different possibilities. The math we use to describe this is something called Hermitian operators. In short, the wave function defines the system, and measurements are probabilistic. Now I am ready to discuss Postulate 4 of quantum mechanics. I'm going to read Postulate 4 exactly as textbooks write it. The goal of this video is to make the words I'm about to read make sense. After you hear the textbook wording, we'll unpack it with clear examples and visuals. Postulate 4, the state reduction postulate. If a measurement of A yields the result a, the state immediately after measurement is the normalized projection of psi onto the eigenbasis associated with a. This is a mathematical equation representing that statement. P sub n is the projection operator onto the eigenspace V sub n. This equation is often called the wave function collapse. For the rest of the presentation, I will focus on explaining this postulate in a more accessible way. Now I want to move on to discuss the first of three examples to help explain Postulate 4 and the measurement problem of quantum mechanics. This example involves measuring the position of a particle in a one-dimensional box. And so the measurement we'll be talking about here is measuring the location of the particle. For this example, I won't define measurement in full detail. For now, just think of it as the act of finding where the particle is. In the next applet, we'll explore a concrete example of measurement using a magnetic field and a detection screen. This red spiraling line represents the wave function for the particle in the one-dimensional box. Before measurement, the particle is spread out everywhere along this line. This region is very small, roughly the size of an atom. This means the particle isn't sitting at one spot. Instead, it has a range of possible locations, each with its own probability. In this applet, the wave function is built from 3 corkscrew-like waves, each with a different wavelength. I can click this component button, and this lets us see the 3 different waves. These 3 boxes, lambda 1, lambda 2, and lambda 3, tell how many wavelengths there are for each one of the constituent waves. For example, if I change this 11 to 50 and hit apply parameter, now you can see there are 50 wavelengths for this wave, which I'm calling lambda 2. P1, P2, and P3 show how much of each wave contribute to the overall wave function. I'm going to click the component button again and hide the individual waves that combine to form the total wave function. And I'll change this number back to 11. These black vectors represent the complex numbers that make up the wave. This is the real axis, this is the imaginary axis, and this is the x-axis where the particle can be found. Below the wave, you'll see 10 sample points along the x-axis plotted in boxes. Each represents one complex number in space, a small snapshot of how the wave function behaves. These 10 numbers correspond to these 10 black dots along the line. In reality, the particle can be found at any point along this line, not just at 10 points. I've chosen to sample just 10 points to help illustrate the idea. If I make a measurement, the wave function collapses. Now the particle is just at this location. You can see this is the only vector that exists. The particle's smooth, spread out probability cloud suddenly collapses into a single point. The particle is found at one definite spot. At that instant, its position is known exactly, but its momentum becomes completely uncertain, spread over all possible momentum values. I reset the wave function. Once again, the particle is in a probability distribution along this line, and if I make a measurement, all of a sudden the wave function collapses, and now the particle is found at this location. In this applet, The collapse is shown by the vector's length suddenly jumping to 1 at the moment of measurement. Quantum mechanics can predict the odds of each outcome, but not which one will actually occur. The measurement problem comes from this mystery. The math tells us the probabilities perfectly, but not how or why the wave suddenly collapses from many possibilities to one real outcome. Now I will move on to a second example demonstrating postulate 4 and the measurement problem. In this example, I'll discuss how we measure the z component of angular momentum of a tiny particle. Imagine a tiny spinning charged sphere rotating about an axis that runs through its center, just like the Earth spins on its own axis from the North to South Pole. Now shrink that idea down to something unimaginably small. That's the classical picture of a spinning charged particle. In this animation, imagine a tiny spinning charged particle at the origin. The arrow shows the direction of the spin axis, the line about which the particle is rotating. No one has ever actually seen an electron or proton spinning. This is just a helpful model. Don't take the picture too literally. Think of it as a tool for understanding.
The sliders let you adjust the direction of the spin axis without changing how fast it rotates. As you move them, you're changing the angles the spin axis makes with the x-axis and the z-axis. The arrow shows the spin vector the direction the particle is spinning around. Once you've chosen the spin direction, press Translate to send the particle into the magnetic field.
Imagine sending tiny spinning particles, silver atoms, into a magnetic field that's stronger at the top than it is at the bottom. Because the field isn't uniform, each particle experiences a force that depends on how its spin is oriented relative to the field. The z component of angular momentum, or the projection of the spin onto the z-axis, determines whether it's pushed upward or pushed downward, and how strong that push is. In classical physics, the spin could take any angle between 0 and 360 degrees, producing a continuous range of forces. For example, two upward pointing spins would both deflect upward, but the one more closely aligned with the field would rise higher.
acephysics.org, Math and Physics Tutoring with Dr. Hudis.
The spins are sent into a magnetic field, and they're deflected upward or downward, and there's a screen at the end. When the particles hit the screen, that's the measurement. Each impact on the detector counts as a measurement. That's the moment the particle's position and z component of angular momentum is recorded. With spins pointing in all directions, you would expect a smooth band of impacts across the screen. Here are the actual results from the Stern-Gerlach experiment. This was performed first in 1922. You can see two distinct lines corresponding to only two spin values, not a full range. The classical expectation, shown in the lower illustration, would be a continuous oval-shaped region of impacts. Instead, there is a clear gap in the data, and experiments like this have been repeated countless times in physics laboratories, always showing the same results. Quantum mechanics explains this striking pattern. Angular momentum is quantized. For a spin 1/2 particle, only two orientations are possible. Spin up, which has a 54.7 degree angle with the positive z-axis, or spin down, which has a 54.7 degree angle with the negative z-axis. There is no middle ground. Nature allows only two outcomes. I want to discuss the Stern-Gerlach experiment introduced on the previous slides in more detail. It begins with a furnace full of neutral silver atoms, heated and shot out like tiny cannonballs through a non-uniform magnetic field, stronger at the top than at the bottom. This is the screen, which is the detector where the measurement is made. Before the atoms reach the detector screen, each one's spin isn't simply up or down. It's in a superposition, a blend of both possibilities at once. The wave function describes the odds of each outcome, but not which one will occur. Before the spin 1/2 particle hit the screen, it was both spin up and spin down, as well as location up and location down at the same time. Once it hits the screen, a measurement is made, and the wave function collapses, and the particle is suddenly 100% spin up at the up location in space, or 100% spin down at the down location in space.
Right before detection, each atom was in both states at once. The instant it hits, it becomes one or the other. How that choice happens, how the wave function collapses, remains one of the great unsolved mysteries of quantum mechanics, known as the measurement problem. That's the essence of quantum measurement.
For the final example in this video, I want to discuss measuring momentum. Before a measurement is made, the system can exist in a range of possible momentum states. In this applet, this is the wave function. It's built from 3 quantum waves with different wavelengths. It doesn't have to be just 3, it could be many more or less, but I've chosen 3 for this applet. Each component wave represents a specific momentum value. The overall wave function describes a probability distribution, but when a measurement of momentum occurs, the distribution suddenly collapses into a single, definite momentum value. This is a wave function corresponding to one single momentum state. Notice one momentum state corresponds to many different position states. If the particle is in this one momentum state, it's in a probability distribution of position values. It can be found at all these different positions along the line, but only one momentum.
This collapse is abrupt, non-deterministic, and non-local. Schrödinger's equation predicts smooth, continuous, and deterministic evolution of probability. The wave function collapse is what gives rise to the measurement problem, one of the great mysteries of quantum mechanics. The Schrödinger equation itself never predicts a collapse. It only provides probabilities for the different outcomes. The act of measurement and the mechanism by which the wave function suddenly becomes one definite state are not actually included in the theory. Physicists can calculate the probabilities of outcomes with great precision, yet no one truly understands how or why the wave function collapses.
acephysics.org. Math and Physics Tutoring with Dr. H. acephysics.org. Math and Physics Tutoring with Dr. Hudis.